In addition to testing hypotheses concerning the mean of a single population, t-tests can be used to test whether two populations have the same mean. For the two-sample t-test, we gather two independent random samples. You take a random sample from one group and a random sample from another. Our null hypothesis will usually be that the means of the two populations are equal. The null hypothesis is that the mean from group 1 minus the mean from group 2 equals 0. But if we wanted to, we could also test to see whether this difference equals some number, like mu1 minus mu2 equals 4. But you're pretty much always testing equality of means. Your null hypothesis will almost always be that this difference equals 0. We assume that the null hypothesis is true. If it is, then this statistic follows a t-distribution, and we can compute probabilities associated with it by using a t-distribution curve. In the one-sample case, the degrees of freedom are n minus 1. Here, it's more complicated because we have the two n's. We could have different sample sizes from each group. To get the degrees of freedom, you can take the minimum of n1 and n2, that's what this notation is here. Whichever of the two is lower, subtract 1 from it. This is the method the book recommends for when you're doing it by hand. R uses what's called the Satterthwaite approximation to get the degrees of freedom. And you can look up this formula. It's not that complicated, but it's more work than you'd want to do by hand. So if you're performing a two-sample t-test by hand, use this method. But be aware that your results may be a little different from what you'd get using software. The assumptions of the two-sample t-test are similar to those of the one-sample test. We assume our observations are independent. Within each group, the observations are independent of each other. Each observation is independent of the observations in the other group as well. Next time, we'll look at the paired t-test, where we assume independence within groups but not between them. For this test, though, we assume that we have within group and between group independence. And this is generally accomplished by randomly sampling from two distinct populations. We also have a normality assumption. The t-distribution arises from a standard normal distribution, so we need a normal random variable in the mix. In order for x bar 1 minus x bar 2 to have a normal distribution, we need both x bar 1 and x bar 2 to be normal. So for both samples, we need to check that either the central limit theorem has kicked in, which means that sample sizes are above 30, or that the population itself seems normal. And we can check that with a histogram of the sample. And here's how you calculate the confidence interval. It's just like in the one sample case. Our estimate for the difference in population means is the difference in sample means. So our interval is centered at the difference in sample means. Then we find a t-critical value with the appropriate degrees of freedom. Multiply that by the standard error. Add and subtract it to this to get the interval. Here's an example. I based this on an exercise in the book, but I changed the number slightly so I could have data that I could use with R's t-test command. R has a built-in data set called MTCars, and that's where the numbers in the table come from. We want to see if cars with manual transmissions get different gas mileage from cars with automatic transmissions. A manual transmission is a stick shift, if you've ever seen one of those. Our null hypothesis will be that the difference in population means is 0. We assume that the mean gas mileage for all manual transmissions is the same as the mean for all automatic transmissions.
we're testing for a difference. So our alternative hypothesis is that this difference is not equal to 0. This is a two-sided test. If we thought that manual transmissions get better gas mileage, we could do a one-sided test to see if this difference is greater than 0, which would mean but that's not what we're doing. We're doing a two-sided test here.
We should always check that the assumptions of our test have been met. We'll assume independence because I don't know how these cars were sampled. The central limit theorem will work if n is greater than or equal to 30 and there are no extreme outliers. But both samples have less than 30 observations. Histograms of the two samples show no major departures from normality, so we'll assume that these were drawn from normal populations and proceed with the test. The automatic histogram might not look so normal, and in fact this was the most normal I could get it to look. But the sample size is small, and we could easily draw a sample of size 19 that looks like this from a normal distribution, so it should be fine.
I compute the test statistic according to the formula. Under the null hypothesis, this statistic follows a t-distribution. I'm doing this by hand, so I'll get the degrees of freedom from the minimum sample size method. The smallest sample size is 13. 13 minus 1 equals 12. My degrees of freedom are 12. The t-statistic is 3.76. It landed here. The probability of drawing a statistic that extreme in the greater than direction when the null hypothesis is true is the area ahead of 3.76. We double that to get the area that's just as unlikely on the other side. The p-value comes out to be 0.0027. This is very low. It's unlikely we would see a statistic like this by chance. Because it's lower than our significance level, which is 0.02 in this case, we reject the null hypothesis. We conclude that there is a difference in the population mean gas mileage of manual and automatic cars. Here's the calculation for the confidence interval. It's a 98% interval. We usually do 95, but that means I want the 99th percentile of a T12 distribution for the critical value. That's because the middle 98% of the area goes from the first percentile to the 99th. I find that number using the QT command in R. I multiply that by the standard error. Add it to the difference in sample means to get the upper bound, subtract it to get the lower bound. We are 98% confident that the population mean gas mileage of cars with manual transmissions is between 2.08 miles per gallon and 12.4 miles per gallon higher than the population mean gas mileage of cars with automatic transmissions. And you need to pay attention to the direction of subtraction. We subtracted manual minus automatic, but we could have just as easily chosen automatic minus manual. Everything would work the same, but the bounds of the confidence interval are negative. We are 98% confident that the population difference is between these negative numbers. That's telling us that automatics get lower gas mileage. It's the exact same thing, you just need to pay attention to how you interpret the difference. The t-test command built into R only works with data. If all you have are the summary statistics in a table, you would need to calculate everything yourself the way I just did, or find a package to do it for you like this one. In this case, I have the data, and the syntax is t-test continuous variable squiggle grouping variable. It's just like the syntax for the box plot. This is the variable we're testing, the gas mileage, and the variable that determines the group is this one, AM for automatic manual. This code will run in R if you try it. The empty cars data is built in.
But I set the confidence level to 0.98, and my output is shown to the right. The t statistic is the same thing. Ours is a little more accurate due to rounding. The p-value and confidence intervals are a little bit off, but that's because the degrees of freedom for the t-distribution they're using is 18.332, and that comes from the Satterthwaite approximation. I would say use R's approach to finding the degrees of freedom if you can, and only use the minimum sample size minus 1 if you have to. If we have good reason to believe that the population standard deviations are equal, we can get a somewhat better estimate of the standard error by using the pooled version. Instead of using this, use this. And the degrees of freedom are n1 plus n2 minus 2. In R, you add pooled equals true to the t-test argument. You should only use the pooled version if you have a good non-statistical reason to believe that the population standard deviations are the same. If you take two samples and they have similar standard deviations, that's not reason in itself to use the pooled version, because then you're letting your data determine the course of the analysis, and that's bad. When the population standard deviations are equal, the pooled version is often only a slight improvement over the unpooled version. To be on the safe side, we usually avoid making assumptions that we don't need and just stick with the unpooled version. But there are cases where the pooled version is useful. In ANOVA, which we might get to later, you test a bunch of different groups with something called an F-test, and then you test pairs separately with t-tests. The assumption of the F-test is that all groups have the same population standard deviation, so you should keep that assumption when you do the t-tests. Anyway, this ANOVA scenario is where you're most likely to see the pooled version of the t-test.